myself Ramrade. I am from Electrical and Communication Engineering Department, and the subject is microprocessor and microcontroller. And topic is about a flexible architecture for scalable spin Q-tube control. Introduction to spin Q-tube control. Spin Q-tubes are the promising candidates for quantum computing due to their long coherence times. Scalability of control architecture is essential for practical quantum. This presentation explores the enhanced scalability in spin Q-tube systems. Fundamental of spin Q-tubes. Spin Q-tubes utilize the intrinsic angular momentum of electrons or nuclei. Control is achieved through magnetic or electric fields, enabling the quantum operations. Reliable manipulations and readout are critical for quantum gate fidelity. Flexible architecture for scalable spin Q-tube control typically errors to the efficient and extensible management of spin Q-tube in quantum computing. Escape. Large number of Q-tubes below in the breakdown of what such an architecture might be challenges to addresses and why it matters. Overview. Spin Q-tubes often hosted in the quantum dots or donor atoms are promising candidates computing due to long coherence times. Compatibility with CMOS with technology, high fidelity operations. However, controlling many spin Q-tubes poses significant challenges in wiring and the delivery and the crosstalk, especially at cyanogenic temperatures. Fundamentals of spin Q-tubes. Spin Q-tubes utilize the intrinsic angular momentum of electrons or nuclei. Control is achieved through magnetic or electric fields, enabling quantum operations. Reliable manipulations and readout are critical for quantum gate fidelity. Key components of a flexible architecture: modular control units, cryogenic compatibility, multiplexing techniques, digital backend, software abstraction layer, error mitigation and real-time feedback. Need for a flexible control architecture. Flexibility allows adaptation to various Q-tube technologies and configurations. Modular designs facilitate scaling and the maintenance of large Q-tube arrays. A scalable architecture must balance performance, cost and complexity. Core principles of flexible architecture. Modular design with interchangeable components enhance adaptability. Hierarchical control systems enable efficient control management of large arrays. Integration of classical and the quantum control electrons is a vital for responsiveness. Scalability strategies. Hierarchical control network. The tree-like architecture for distributing signals and the processing feedback. Crossbar networks allow reconfigurable the routing of control signals of Q-tubes. Allow configurable routing of control systems to Q-tubes. Shared resources scheduling. Efficient scheduling algorithm to time share expensive control hardware. Hardware components of the flexible systems. Quantum control hardware includes microwave resources, pulse generator and amplifiers. Classical control interface manage Q-tube initialization, manipulation and the measurement. Advancement interconnects support high density integration and the signal routing. Research trends and the examples. Several ongoing effects and the proposals from both academic and industrial labs. Intel's Cryo CMOS control chips for spin Q-tubes. QTEX QMA, a micro architecture for quantum control. MIT Lincoln Labs scalable control electronics for silicon skin Q-tubes. Zurich Instruments and the Blue Force integrating cryo compatible signal generation processors. And the challenges: signal integrity and the noise at cryogenic temperatures, calibration drift and the variability across Q-tubes. Integration with error correction scheme. Power dissipation limits in the cryogenic environment. Why it matters: building a flexible scalable control architecture is a critical for transitioning spin scalable demonstrations to full-scale fault-tolerant quantum computers. The architecture performs thermal constraints and the resources sharing while remaining adaptability technologies and the software requirements. And some of the hardware components of a flexible system are the quantum control of the hardware includes microwave sources, pulse generator and the amplifiers. Classical control interfaces manage qutb initialization, manipulation and the measurement. Advancement interconnection support high density integration and the signal routing. Software control strategies. Software framework coordinate multi qutb operations and the correction and the error correction. Dynamic calibration routines adjust control parameters in the real time. Open source and the modular software promote adaptability across different hardware setups. These are the software control strategies. In the figure we can see also the diagram of the software control strategies. And the modular control electronics use the FPGA based modules allows customization for specific qutb types. Reconfigurable electronics enable rapid adjustments to control sequences. Distributed control units reduce latency and improve scalability. These are the modular of the control electronics. In the modular control electronics, we can use of the FPGA based on the modules allows customization for specific qutb types. Reconfigurable electronic enable rapid adjustments to control sequences. Distributed control units reduce latency and improve scalability. Hierarchical control architecture. Local controllers manage small groups of qutbs and the fast operations. Higher level controllers coordinates multi-group interactions and the error correction. This hierarchy simplifies system complexity and enhances scalability. Local controllers manage small groups of qutbs for faster operations. Higher level controllers coordinate multi-group interactions and the error correction. This hierarchy simplifies systems complexity and enhances scalability. Signal routing and the interconnections. Flexible interconnections facilitate dynamic reconfigurable of the control pathways. Coaxial waveguide and the integrated on-chip routing solutions are employed, reducing crosstalk and the loss in control critical for maintaining high facility control. Integration with quantum error correction. Control architecture must support real-time error detection and the correction. Modular design allows dedicated hardware for error correction routines. Scalability depends on the efficiency implementation of a fault-tolerant protocols. Control architecture must support real-time error detection and the correction. Case study. Scalable spin qutb arrays. Example: architecture demonstrate multi-qutb control with minimal crosstalk. Modular control units can enable expansion to hundreds of qutb. Adaptive control schemes improve overall system fidelity and the resources. Future directions in the flexible control architecture. Developing on the chip integration, reduce physical footprint. Leveraging machine learning for adaptive control and the calibration. Exploring hybrid architectures, combining different qutb types for optimal performance. Challenges and the limitations. Managing thermal and the electromagnetic interface remains complex. Ensuring synchronization across large system demands precise timing. Cost and the complexity of highly integrated systems pose practical hurdles. And the conclusion. Flexible architecture are visit for the scalable control of spin qutbs. Modular and the hierarchical designs offer pathways towards large-scale quantum processors. Continued research and the development are essential to overcome current limitations. Summary of the key takeaways. Scalability requires adaptable hardware and the software control solutions. Modular components and the hierarchical control facilitate system expansion. Integration and the calibration are critical for maintaining high fidelity qutb operations. Acknowledgements and references. Acknowledge contributes from research terms and the funding agencies. Refer to recent publications and the ongoing projects in the scalable spin control. Invite collaboration and the discussion in the advanced field further. This is the conclusion of the flexible